All right, everybody. Welcome to your first weekly webinar with Michael Floyd. I am your mentor and your mentee. You learn as much from me as I learn from you. All right, let's talk about the first thing, which is setting the pace for this course. One thing I don't want anybody to fall behind early. I mean, as best as possible. If you're up ahead early in case something happens, that is great. What tends to happen is, everything happens, it seems, whenever you start something new, right? Family problems, harder coursework, but, you only get a shot at this. You've already paid your money. Not sure if you can even take another shot, so you might as well try to hurry up and get everything done. If you are in the room, in the chat room, just give a shout out. Let us know you are here. I will be viewing the group chat. And one thing I got to say for everybody, anybody who's behind right now, I know I was giving weekly instructions, but perhaps something good is if we can wake up 30 minutes and just knock out 30 minutes. And right before we go to bed, just knock out 30 minutes. That might give a better insight on, how to proceed with this, right? So it's 30 minutes, 1 hour a day, 7 hours. You are more than ahead and you can catch up, right? And maybe every time you spend some time in order to get the classroom involved. I don't see enough participation in the groups. I would like every time you spend time on this for you to just say, hey, I spent 30 minutes. I learned about this. I'm almost done the lesson. I'm comfortable, not comfortable. Just, keep writing in the chat room. I want the chat rooms to start buzzing. And, when you don't report Sunday, what you've done, I cry a little inside. I feel like you're not a part of the team. I want this to be a team effort, okay? And one thing you don't want to do is see a grown man crying. I can tell you that. It is not a pretty sight. So, keep a grown man from crying. Report Sundays. Try to get 30 minutes in, morning, night, and I am confident we will catch up or knock this out and knock this out of the park. All right. This weekly webinar is focused on regression and classification. I know they had lessons on regression and classification. I know most of y'all did not get to everything dealing with classification. I will only cover as far as the decision trees. I know we are still looking at support vectors and naive Bayes, which I cover for a later time. And I also did a tutorial on Bayes' theorem that you might like that I will also post the link to on the channels that we are using. But I will begin talking about regression. Okay, let me share my screen. All right. So I believe my screen is being shared right now. Okay. So regressions deal with continuous data. So that is ratio data, which has zeros, interval data, which, it doesn't have zero, like profits and whatnot, and some oral data, like maybe how hot is the pepper from a scale of 0 to 10. That could be something as well. And the first thing I was going to do, thanks to a question from one of these students, is to explain some of the Python code that is in the linear regression module. And Python can be a new language to some of you. Sometimes it's important to understand the functions and how everything goes. So I will explain number 18 in lesson 2, which number 18 is generate a predictor from BMI and life data. So you have 3 columns: country, life expectancy, BMI, and the problem is to build a model with predicting life expectancy from body mass index. So country is not necessarily used, but just to show exactly what happens, we have a CSV. CSV has titles to the columns, and it also has life expectancy and the BMIs uh, from the countries. Look at these solutions. So our first thing we do is we import all of our statements we need. So we import pandas, we import the linear regression model we need from sklearn, and after that we import the data. So we use Panda to read the CSV in, BMI life expectancy. Pandas recognizes that it has headers, and then we fit the linear regression model. So we generate the linear regression model, we call it BMI life model, and then we fit the data. So what we are fitting is we're fitting the BMI and our Y values, which we're predicting life expectancy. So BMI is the only column, and as predicted, and life expectancy is the Y value. And now we are making a prediction using the model. So all we want to do is predict the life expectancy with a BMI value of 21.70931. And as you can see, it does not tell you the answer, but if I paste in here and I test run, I will get a value of 60. So based on the data from many countries, a BMI value of 21 will give us a life expectancy of 60. All right, and that's just a simple example, and I'll run through the code with Python. All right. So what you generally see with regression and these classifications is what we're trying to do is we're trying to find relationships, and based on those relationships, then generate functions that will allow us to accurately predict what will happen with the data. With regression, of course, we find that our functions, are what gives us the predictors, right? So the actual slope, the intercept, or whatnot tells us, about the functional classification. We'll see that, the functions are what separate the classes. But now going to um, show you here, just so this is an example of regression, linear regression, which is one predictor. It's easier to see in two-dimensional space. But so what we have is we have a whole bunch of data points. And as you can tell, it looks pretty correlated, which means it looks like there is a relationship between the X values and Y values. Of course, not completely correlated. There does seem to be some error or some variance within this, but yes, there does seem to be correlation. And the line that is drawn is actually the line that uh, uh, is the line that minimizes the mean squared error. One and yeah. And here, in case you should generally understand the mathematics behind it, because the mathematics, when the inferences don't hold, or when you might need to change the model a little bit, understanding mathematics in order to redefine the model is helpful. But here's the mathematics for the two-dimensional solution. You minimize the error with respect to the weights W1 and W2, which in this case is just the slope and intercept for one variable x. So we minimize the slope and intercept. We come up with these equations that minimize the slope and intercept and set the derivative to 0. And that is pretty much gives you W1 and W2. Yeah. Okay. And here it is for n-dimensional. So n-dimensional, you have x rows, which tells you the number of observations you have, and n columns, which tells you the number of predictors you have. And applying the same thing, which we have an error, and we want to minimize our error, and then set minimizing our error equal to 0. So we end up having this equation that tells us the weights that are assigned to all of the predictors. And 24, which is polynomial regression. I'm not trying to play the video, I just want to show you the lines. So at times, the data will not be exactly linear, right? Many times you'll see maybe periods of oscillations within the data. So that the data will be exponential, logarithmic, polynomial in this case. There are many uses to which transforming the data is best whenever you're trying to fit a model. A lot of times the transforming, takes looking at, it takes intuition in most cases. Most cases you will have an idea, right? So if you're trying to plot uh, acceleration, acceleration is, it has to do with a squared time, right? So perhaps if using acceleration, you have the squared of time, right? So some things as far as that will need require higher degrees of polynomial regression and can be observed through the data and through the errors actually. So one thing that the lessons did not cover uh, is when when can you use these polynomial um, regressions and how to observe when to use something else. And this is from a data analysis class that I took a while ago. And what it pretty much is going to show you exactly uh, through diagnostics, which we call. So once you fit the model, you have to diagnose whether the model actually um, fits the predictions well, or if you could do anything to make the model fit the predictions better. Okay, so um, the residuals, which is just the predictions minus the actual values. They will all sum to be 0, but there's things about these residuals that we can use in order to determine uh, whether there needs to be transformations or whether the model actually fits, right? And The first thing is nonlinearity. We're going to discuss. Okay, so nonlinearity. Um, this is as far as the predictor variables. It can be seen based on a plot between the residuals and the fitted values. A lot of the time, you will have multiple predictors, so you'll have a large dimensional space. But if you can plot the residuals versus the fitted values, you should see something similar to this, right? And a scatter plot with the response and predictor should be similar to this, right? So you don't really see any differences, or you can't discern any noticeable pattern between the residuals and the fitted values. And this is the line zero. Remember, so the sum of all the error terms um, should be equal to zero. Um, and this is an example of residuals versus fitted values that does not look proper. So what you see is you see a high residuals and it dips down and it goes up, right? And you can see that from versus fitted. You can also see it a little bit when you plot the responses to the predictors, right? So here you can tell that there is something wrong and perhaps a transformation is needed. And this is just a basic look of, this is how, of course, residuals is supposed to look. So you're not supposed to have any pattern between residuals and fitted. And this is trouble whenever you have, whenever you're applying the residuals and the fitted values. And heteroscedasticity means that, there is something we could possibly do with the y values, because uh, the it's the variance in the error. So it's the checking whether there is a transformation that can be done to the predicting variable or variables. So we plot the residuals against the predictor, uh, and this is of course the same thing. This example of where heteroscedasticity is not there, and this is an example where there is definite heteroscedasticity. What you see it bunched up initially on the predictor or the fitted value. Then you see it expanding as far as variance. So you do not see a consistent pattern as far as the variance of the model. And you can see that right here as well. You see it very, very close to the line, and you see the variance fanning out, spreading out, which is what it's not supposed to do. It's supposed to be generally consistent as far as the errors are concerned throughout the model. And here are some examples with the yellow again. So you see, this is what you want. This is what you do not want, right? You're starting out small and generating large variance and going towards small. And outliers, the lessons did touch on outliers as well. Outliers can affect your model by shifting it in one direction or the other just based on a couple of observations. Now, what you can do is, it's typically up to what you are doing and documenting as to whether you want to remove the outliers, whether you possibly normalize or standardize the data. All these are options that you have when you have the presence of outliers. But based on what you are predicting, that should be your decision as to what to do with the outliers. Or you can just keep them in the model. Some things you might need. These outliers might be necessity, and you keep them in the model. But they can or cannot be problems depending on whether your model says you should keep or discard them, right? So depending on whether what you were modeling, you believe you should keep or discard them. And non-independence of error terms. This is an example of a errors that are affected. Or residuals that are affected over time, right? So that's not what you want as well. You do not want residuals affected over time. What you want is, this is even worse. This is a sinusoidal pattern of residuals affected over time. You don't want, in both of those cases, to see residuals in those ways, right? And uh, box plots, histograms, and QQ plots are ways to check whether the residuals are not normal. And as you can see from the first one, the residuals are pretty normal. So the QQ plot, the residuals seem to lie on this line, and there's no discernible pattern. But here you see they kind of span and go up, which is what you do not want to see as far as a QQ plot. I will say something about the normality of residuals before you attempt to um, do anything as far as um, the assumption of normality for residuals. Whenever the residuals appear non-normal, it is usually because of one of the other previous terms. The heteroscedasticity, the non-normality of the fitted values. It's usually one of the previous terms, and checking and fixing those can usually cause to your residuals being normal. But these are things you uh, don't want to see, which is a lot of outliers for the residuals. Um, yes. And what to do when you have this? Okay, this is just an example. The QQ plots right here. Um, so these are the same three plots except uh, zoomed in. So what you see is you have these outliers, which you definitely do not want the outliers here, which is actually making very, very large, this plot very large. You have this more zoomed in right here, which you can more see the curvature, and this is zoomed even more, and you can observe the uh, curvature again. All right. So, remedial measures, right? Um, One, you ban on the simple linear regression, which is what you learned as far as polynomials. You can use sinusoidal, anything as far as what your intuition tells you, or you can employ, which are transformations in and of themselves, or you can employ a transformation um, you know, based on what I'm about to show you right here. So the first thing for nonlinear predictive values like this, right? If you can see if the regression, if the pattern of the fitted and the residuals look like this, perhaps x should be a log, or take the square root of all the x values. If it looks like this, perhaps a squared or exponential, and maybe like this, a 1 over x, or a negative exponential of x could be the something that you do as far as transforming the data. Uh, and we'll look at an example of this. The example is in R, but the concept still applies the same. So, and of course, with the logarithm and the taking the 1 over the values, whenever you're dividing by 0, right? Of course, you can't divide by 0. So just adding a small constant, making sure there's no divisions by 0 or anything to that nature, no problems. Negatives would be, of course, great. Optimal. So, and this is the transformations of the y values when you see the unequal variances, right? So remember what we saw before. We saw the variances have small variance and then go to large variance. A square root function could be used from large to small, a log function, and this is also some small to big. Similarly, a what as it's not exponentially growing like this one, but 1/y is also something that could be used as well. And the same thing, constant involved. Make sure there's no dividing by zeros or negative logarithms as well. Um, and the Box-Cox transformation, which the lambda, when you solve for lambda, the lambdas will tell you how to transform the data. You generally stay away from polynomial regressions above 2 because they can get complicated unless there is reason to go above 2. But this is just some of the examples. And, the Box-Cox is going to give you a number. And based on where that number is, let's say that number is 0.6, taking a y to the power of 0.6, like we're seeing right here, y to the power of 0.6, you might as well do y to the power of 0.5 because the square root of y is more interpretable than 0.6. And you see for lambda equals 0, it's not just y to the first, y to the 0 power, which y is 1. You take the logarithm of y. And one thing it doesn't show is lambda equals 1, and lambda equals 1 is just y. So, and this is an example. And also x can have a lambda function as well, but that's just an observation of what it looked like with just y. So, a couple of factors you can go back and read through this. I will post these notes in the shared folder or in a shared folder. I'm not particularly sure. I'll have to ask whether you can have access to the content in the shared folder, but I'll make the content public and post the notes. But this is an example I wanted to give. Example that was in the textbook. So plutonium measurements. So you have plutonium, you have the alpha count, and you have the activity of these measurements. And just a better thing to look at is the plot. I'm not a plutonium expert, but here you have the number per second, and you have the I believe this is plutonium in grams, the alpha count and activity. So as you can see, this is the activity. This is the alpha count of the plutonium, and the goal is to plot a line, of course, based on the activity. Try to fit the best regression line for the alpha count. So, of course, we do first just fit a model. So you see, fit a model. This is just looking at the. This is the okay. This is the model. You have the intercept, the activity, and those are the parameters involved. Those are the weights that were obtained through the mean square error, the 24 observations, and now so we plot the residuals and the fitted values, and here's the residuals to the fitted values, and here is a normal QQ plot. So the QQ plot, it does stray away. This is kind of normal, and you see the tails go up right here, it goes down here. So it does say that, hey, maybe the residuals are non-normalized. But before we do anything to fix the non-normalization of residuals, of course, remember that we try to uh, see what can be possibly wrong as far as heteroscedasticity and nonlinearity of the x values. What we see here is we have a fanning out, right? So we have a smaller amount of variance in the residuals, and the farther we get up, we see we have a much larger variance. And so remember, this is fixed by the y values being either a square root function or one divided by the y values. I apologize if it is noisy a little bit. I am in a coffee shop, but uh, what we do is we do a Box-Cox transformation in order to see exactly what measures should be taken. So we have the Box-Cox. We look at the 95% interval for this Box-Cox transformation, and we see in the 95% interval this is 0.6, but 0.5 is within the 95% interval. We could use this number right here. This number right here is this number right here is I can't find the number right there. It's 0.6 something. Okay, it's around 0.65, but we don't tend to not taking an exponent to 0.65 is not something we get generally more or less understand easier than just taking these square roots. So we take the square root of all of the y values, which y values are what we're trying to predict. Take the square root of all the y values, and then fit a model based on the square roots of all of the y values. In this case, the alpha levels of the plutonium. So now we fit a new model with the square root of the alpha count, and then now we have new intercepts activity, and what we do from there is we look again at the residuals, the fitted values, and the QQ plot. The QQ plot, as you can see, it's looking a lot better, right? But if we look at the residuals, we do see kind of a decrease, then an increase, and then a slight decrease. And before when we did it, we did see that there was linearity, although the variance was bigger. But now, because we took the square root of y, we can see that there is a problem with x. So possibly x needs something done as well, right? So given we took the square root of y, and before we took the square root of y, we did not have any problems with the with the residuals being nonlinear. If we take the square root of x, we should now have residuals that are linear again. So we take the square root of x now in this case as well. And also, as we can tell, when we have when it goes positive, when it goes down, it goes up like this, based on what we saw earlier. With nonlinearity, taking the square root can help that as well. So right, we will take the square root of x based on the square root of x and the square root of y. Now, this is the square root of the predicting and the predictors. And now we fit the intercepts. and well, we find the intercepts based on the finding the least mean squared error, and we now plot the residuals, the fitted, and the QQ plot. As you can see, the QQ plot, not too much deviation from the QQ plot. So if it's not normal, then it's all right, because what did we do? We didn't use exactly 0.65. We used square root, which is better. And now we see we have pretty consistent variance throughout, right? So nothing we can really say is a general major concern with the variance. Nothing different with the residual values being nonlinear, and we can say the residuals look pretty normalized. So that would be an example of transforming the data and making sure that everything is fine. And this is an example of what it looks like taking the square root of the alpha count and the activity. And as you can see, this looks a lot better than the previous graph. So here's the graph. You don't see too much variance in these levels. And let me just finish up before I go back there. So this is the end model that we would use, and this is the graph. And this was the initial values, right? So remember, we had really small variance in these values and really large, the larger it goes. So as you can see, what we did is we made sure, except for this outlier, I believe they actually removed the outlier. I didn't even, yeah, so the 24th one was actually outlier. So that's one thing. In this example, they saw this major outlier. They looked back in the lab reports. It should not be there. They removed it. So this outlier was removed, but as you can see from the rest, uh, the variance increased. So to make sure we account for that variance, we did take the square root and we plotted the square roots of the values. That is an example of the transformation when it comes to a simple linear regression. When we talk about multiple regressions, you have to also look at correlation, uh, collinearity. There are many factors involved. Okay, that's just in addition to what the lessons covered as far as regression. And we have classification, and classification deals with discrete data, nominal data, right? So this is a dog, a cat, a car, some ordinal data. So rate, you're happy. Are you happy? You know, happy, excited, super excited. Those things that really don't have specific uh, measurements toward them. There's no specific measurement between happy, extremely happy, those kind of things, ordinal. That's what classification generally, these kind of problems. Well, those are classified as classification problems, and classification is just like regression. So you find relationships within the predictors that can help you make predictions. So that is pretty much classification as well. It's all about finding these relationships, and also, big part of machine learning is making sure the relationships do make sense, because you doing model after model, and of course there are going to be times where you might find something correlated or relationship, and it shouldn't be there. It's possibly just you know. It's cool, but it will not make sense. So a big part about machine learning also is to make sure what you're looking at does make sense, but to find those relationships. And I believe four. So yeah, four linear boundaries. So this is an example This is a perceptron. Perceptrons are more used in neural networks, and when you have multiple inputs into the perceptron and you actually use activations in order to generate the numbers of the classification and connect them, they get more complicated than a simple perceptron where there is zero activation. And you will learn more about perceptrons uh, as the lessons go along, because they do have uh, a project on image classification. But this is a example of something a perceptron will do. Right? Is you have a classification. You want to classify whether this is blue or red. I think this was accepted into university, not accepted into the university. Right? You have two dimensions. Looking at two dimensions is always easier as far as giving examples than multi-dimensional, but it works the same way in multi-dimensional. So three-dimensional space, you have planes determining where the best cut will be, but you have a line and you want to maximize where the best possible place is to uh, make that decision of whether somebody gets accepted into the university or most likely does not get accepted into the university. Okay, and very straightforward example. Almost all the points are within blue, and all the points within uh, red. So very great example. And decision trees are another great way to classify and also use for regression as well. So, what decision trees, I think I have something up right here actually. What decision trees do is, you start with your uh, data and you make splits based on, of course, your parameters, the size of the nodes, but you make decisions based on the uh, entropy, or which is how much you can gain from how much information knowledge you can obtain from it by making that split in the right place. So, um, for example, if you have, they give better examples in the actually lessons, but um, pretty much this is it. So you cannot hear the volume on this. So what entropy does is entropy tries to make sure that I can hear the volume. Let me turn up the volume so I can't hear. So what entropy does is tries to think of a rule. So if you have, let's say, uh, three reds, one blue, entropy will attempt to think of a rule to where it will split the data to where there's three reds and one blue. Uh, if it can't, of course, it'd be better to have uh, two reds and one red, one blue. But the point is to attempt to make the split in the best way as possible, so as you can maximize your knowledge and make better predictions and decisions based on where your split has been. I know we have not gotten to support vectors yet. Um, there is also a great discussion I've already done on Bayes' theorem that I will also post as well. And that is all I'm going to do as far as screen sharing. And one more thing that I wanted to point out before we go is just some afterthoughts. I'm hoping that we all complete this and, you know, everybody finds a job as far as in the field of data science, and that job is long term. That job is permanent, right? It's in your dream location. You find the dream woman or dream guy, but most of the time these things do not actually occur. So it's best if we also think of what is going to happen after the course, uh, in case you do not find that dream job, right? What are you going to do? One thing I want you to be able to use what you've learned as far as in data science, but create a job for yourself. Just think about ways you can do that. I mean, whether it's mentor, create an online blog, YouTube videos that show examples of things you're doing. There are many things you can be doing just as far as this data science field is new. So there's many things you can be doing as far as to use your credentials and your tools in order to generate an income for yourself and get noticed by different companies. You create teams for hackathons. So, I'd like you to think of something you can do, should do, share it with the groups. If you think it's a great idea, you don't want to share it with the groups, you can share it with just me. I'm not going to take your idea. I do things on the side myself. So, there is an importance into being able to create for yourself and also, of course, acquire as much knowledge as possible. So that is all I'm going to say on that. I will look to, are there any questions? I am not even sure how to find where there are questions. Are there any questions? I invite people, camera, adjust bandwidth, webinar, links, apps, control room, Q&A. Okay, chat. I see it. Are there any questions? Group chat. Can somebody put a message in the group chat to let me know that people are there watching? Is anybody there watching? All right. Let's try in Slack. Okay, can somebody post in the Slack channel and tell me that they are watching this recording? I will give it some time. We have about 10 minutes left. I was going to leave the 10 minutes open for possible questions. Okay. I am not sure how to, well, go right in the check. Okay, it's been a while, about a minute, 2 minutes actually. But I have not heard anything back from anybody in the Slack channel or the group chat, so I will assume everybody's watching and everybody understands and has zero questions, and everybody is doing fantastic and getting on roll with their assignments. Okay, so what I want you to do, of course, we have next Sunday. I want everybody to have completed support vectors by then. And the Sunday after that, completed all the lessons. I think there's only 3.5 hours left after that lesson. So I mean that. So let's just concentrate on this Sunday. Support vectors, and yes, if you have any questions, right, feel free to email, contact me. Feel free to join the groups. And all right, that is it. Thank you.